Excellent. So let's just get started. Any questions?
Is there a way we can see these photos again somehow, or access them, or somehow?
Yes, there is already one folder where we are uploading and making things accessible to you. We will send a circulate an email at some point.
Have you received that yesterday?
Yes, I didn't know if that was just for uploading photos or
Also to download.
Okay.
Yes.
There was a folder, a separate folder for share everyone. The photo is already there. Yes.
Yes.
Okay, great.
It does feel like we've been eating all the time in the photo. That's very true to us. Yeah.
Most important things.
So we are ready for the next session, which is High-Redshift and Cosmology. So our first speaker is Ming. Please, go ahead.
Thank you. My voice is about 30% back, but we'll see how long it'll last. I always wondered why Paul allowed me to do a thesis I did. Never quite figured out what his interests were. It was so different, because I knew I was going to work on time and star formation. It makes a lot of sense after this conference, but nevertheless, we are. I think Paul had different motivation, but my motivation was this paper. I read one of the first papers I read in grad school. And there were lots of things in this thing, a lot of optical astronomy stuff, who cares? But there were a couple of important lines that caught my attention. One was that this explosion involved millions of supernovae. I mean, for an impressionable class student, one supernova was okay, millions of supernovae, oh, that's cool. And then, of course, the clincher was that the nature of the initial explosion in a meteor remains an enigma. It's looking for an answer. There you are. There's a thesis topic. So, of course, first of you can take you on a long journey that you didn't anticipate. I'm not totally sure, Paul, how we decided to go in this direction first. I wanted to know what happened to that galaxy. And it seemed like looking at its environment and maybe the history might be an important thing to look at. So the first big project we did was using H1, the group, 12 field mosaic, the VLA, and later 25 field, which led to a Nature paper. Couldn't find the Nature cover on the internet anymore, so it's about as well as it could do. And then MEU2 has gotten a lot more press lately because of the outflow emanating from the center seen by Spitzer and H-alpha. It's a very, very famous picture, but NRA used to have a museum display where they showed this, and they didn't know who the authors of the papers were. So I had to tell them, hey, that's my paper there. Of course, I think all that information was really visually captivating, and I think it impacted a lot of people's ideas about galaxies being not just item universes, but very dynamic system, dynamic environment, and it's much bigger than what they look like. So this particular picture of the circumgalactic medium, but physical work, I think captures perhaps the work a lot by the study of MEU1 and MEU2, these swirling streams of gas and outflows, cascading cycles. So it sets in sort of the picture of how the galaxies evolve in the whole universe. Of course, now we care about how galaxies evolve over cosmic time. That's my, latest, my passion for the last 20 years. And this is a very well-known poem, of course, by Madame Dickinson, that galaxy evolution peaked around redshift 2, and then at least at that time, it dives down beyond that. I've always shown this picture to demonstrate that We actually have no idea what happens beyond Redshift 2, because we don't actually have data to actually answer that question. But, you know, anything trends, it's either just up, well, there's the start of the universe somewhere, so it has to dive back down. And then the US came up and said, oh, of course, it's obvious. This is what happens because galaxies evolving by gas accretion. And when you look back in time, the universe was denser and more invariant gas form than the stellar form. So this is all that is. And it seems like a reasonable, simple explanation, but these are integrals of a bunch of different functions. So everything boils down to average trends and integral, so which removes any kind of interesting physics ever involved in all that. So I don't think that picture really sums up how galaxies evolve. There could be two completely different tracks galaxies evolve, and we know actually they do, but nevertheless it doesn't quite capture that. Of course, there are also some beautiful cosmological simulations. This is a illustrious TNT50 zoom-in simulation. It's spectacular. I look at this every month just to inspire myself. This particular simulation is on 10 to the 11 point something solar mass. It's a very massive galaxy. It's the only simulation I've ever seen that reached star formation rates of 500 to almost 1,000 solar per year. Most simulations can't quite get to it because, for a number of reasons. Here's a picture of the satellite. This is a picture of gas density. So if you look at this, kind of reminds you of the M81, but it's also very, very different. There are no obvious interaction that you can say about big galaxy maybe interacting with another galaxy or anything like that. This is more like almost continuous inflow, like a giant sink, and you pour the big bucket of water. That's what this looks like. I'll play this one more time, because there's just so much happening in this picture. So, with beautiful images like this, do we really need telescopes to observe anything? Mm-hmm. But again, these things are, as beautiful as they are, they may have nothing to do with reality. Okay, that's just putting it a little bit strongly. I believe the gravity part, because it's hard to mess with gravity. What's not so certain is that almost everything we see are baryons. Baryons just don't act like dark matter. And all the baryonic physics happens on a very small scale, a very short time scale, and none of these simulations quite capture that. They don't have the spatial resolution or the time resolution to meaningfully track physical phenomena like star formation. You also just talk about star formation, right? Well, you'd be horrified. These things have only spatial resolutions of only like 100 parsecs. Anything happens on a small scale, they're just in a box, some magic happened. Feedback, that can be maybe captured properly, but feedback's also starting inside the magic box and by magic. Time scales, 10 to 5 years, maybe 10 to 6 years. Again, all these massive young stars doing all the work. They come and go. In fact, you may not even see it because it's just entering that delta T in time step. There are so many things about this picture that is essentially magic. Some of you contribute to that magic because you tell them what the resolution should be. They have folded in. But exactly how this comes about, I don't think is really that well known. So this is why when JWST went up, for example, the pictures of some of these galaxies, everybody was surprised. Wow, these things are big, they're red, they show up. Oh, you don't see them in Hubble images. Well, like, I remember battling for 10 years with optical astronomy friends that these things are invisible in your deep HST image. Nodding to me. Well, actually, they don't really mean, probably, they don't acknowledge. It's like, oh, it's a new class of object called HSD dark. At any rate. One other ingredient in this picture. One of the reasons that they don't try to go any deeper in resolution is because we'll never reach the resolution relevant for star formation. So 1 arcsecond beyond redshift 1 is about 7 kiloparsecs. 10th of an arcsecond is 0.7 kiloparsecs. So if you're interested in even 100 megaparsec, 100 kiloparsec, 100 parsec, well, you really want to get to like parsec scales to understand star formation and the feedback and all that. I'm sure you all want to do even better than that, and I think you do fantastic work. But for cosmological sources, we have absolutely no hope of reaching those resolutions. So if you can push that a little bit further, that would always help. If you can build a telescope that's 100 meter in diameter, that will also help, but that may not. 100 meter diameter space one observatory, Jennifer, there's a goal for you next. Look at that. But I discovered in my first postdoc years that gravitational lensing can be really cool. We achieved 1 arcsecond resolution imaging of the Caltech quasar in CO76 using West Valley. And then when the images came out, I was like a little bit embarrassed because I divided the line by the redshift, made 2 images, they didn't look like each other. Like, oh man, where did I go wrong? And then I stare for a while and go, oh, that is so cool. Because each redshift side of the line is magnified differently by lensing, so that you expect asymmetry. And so in fact, from that, and with the help of an undergraduate student, Roger Blanford, who had done this mapping for me, we figured that there's about 0.3 arcsecond structure where all this dust continuum is coming from. So even though we didn't quite have the resolution, with the lensing we could infer that these structures are actually pretty small. And it was quite interesting. I did not expect that. So one of the new projects I've started in last, almost exact last decade with an undergraduate student is look for extremely luminous star forming, most intense star forming systems in the universe by looking at Planck whole sky survey in the discard foreground point source bin. We picked out some of the objects that would be consistent with high-redshift galaxies. And we discovered, so far we verified about 30 of them. And my graduate student, Patrick Kamianaski, who is now posted with the Roger course at ASU, has done his thesis basically modeling these systems. So every one of these objects have a typical IR luminosity 10 to the 14. I was sure they were all IR quasars, but none of them are. They're all strongly lensed Einstein rings, and the typical magnification is about factor 10. So these are about 10 to the 13 solar luminosity objects with the star formation rates of several thousand mass per year. And on the left, I mean, this looks like a repeat of itself. On the left, on 0.3 arcsecond resolution does continue. On the right is a VLBI 60 euros image at about similar resolution. And perhaps you all should think that it's totally reasonable that they trace each other. That we find fair correlation holds even at higher redshift. And there they are. It also demonstrates some interesting things. ALMA happens to have a slightly worse resolution than the VLA for that object. Being reconstruct source, it looks a lot bigger and fatter, although there's nothing to do with this underlying source structure. So resolution actually matters a lot. So you meet the conclusion from this work is, let's see if these were really different objects. And I'll do that on that plan and discuss that plot. LIR, corrected for lensing, versus infrared size, source size. These sources are 10 times more luminous than other known infrared sources, including those detected by Herschel, mostly because they're just bigger. They're just bigger. I don't exactly know why they're so much bigger than others. I'll be catching them at a different time. But these are unusual objects. The shaded region is adding to the limited starburst region. Within that region, the star formation will be seized by radiation pressure. None of these things are actually anywhere close to that. So I don't think that has anything to do with it, although we thought there might be a reason. So in every way, they look like pretty normal, crazy starburst galaxy at redshift 2 to 3. Another thing I learned from everybody wants to do like billions samples, physical study of this and that, and MC through just during a spherical cloud of data points. I'll always insisted you learn a lot more by digging deeper into a few pulsating objects. And I think it's definitely holds true for this. And this object is, for the moment, our favorite object to do that. That picture over there is a combination of HSD and a couple of ground-based optical bands. It looks all red because HSD is 1.6 micron. Light from the lens galaxy is very red. My student, Patrick, basically picks out images of either quadruply lensed or doubly lensed and uses those to constrain the foreground lensing potential. It's an isothermal halo with aspect ratio. Now, it's a very, very simple model. We don't do anything fancy, but that's all you need for galaxy lens. On the left there, it shows actually all 30 of our samples. This one's actually one of the less luminous ones. It's a redshift 2.1 to 5. And the force is all mass, star emission rate of 9,000 mass per year. Magnification is about 7. Well, I'm probably eating up all of my time already, so let me just emphasize, creating lensing model is not hard. Whenever we put in like ALMA proposals, someone says you don't know, but the differential lensing is a really pain in the ass, and you can't really constrain things. That's not true at all. Unless you don't think the halo is very different from what we think they are, dark matter halo. Lensing is actually pretty robust. What you don't know about is the time delay. There's a real backlash against gravitational lensing as a tool in astrophysics for a while. There's people trying to use H0, measure H0 through lensing. Running into some issues where if there's a substructure, you can actually drastically change the brightness ratio, and that really messes up your H0 calculation. Here, it is just a simple geometric optics, and even in some degrees, we try also different halo models, NFW versus isothermal halo. It doesn't make a huge difference. Our errors are completely dominated by source structure, basically. So it's been very productive, taking very high angular position HSC data, ALMA data, VLA data, and construct source plane structure. They generally look like spiral disk, but if you did not use lensing, it would look like just a big bloody thing. Now we begin to see substructure. And some of these things look very spectacular. One of the things my former students have been pushing hard is, can you do better? There's a whole molecular line part that I haven't talked about. One of the things, this object, well, I said none of these are QSOs. In radium, there are a couple of bright spots, so we kind of suspect that it might be an AGN. In fact, a couple of evidences suggesting that that source sits in the middle of the spiral-like structure, and it probably is an AGN. And we push the resolution to 10 arc-second. It turns out we recover all the flux, so these structures are really tiny in dimension. And then we do the source construction. We recover basically sources that are significantly smaller. We're getting down to 100 parsec. And polarized objects, we can do better than that. But at the moment, I think this is about as well as one can do spatial scales. So Patrick has 0.1 arcsecond image of all of these things at the moment, but we'll see how the answer bears out in the end. We're moving on to the next stages. This spectacular looking picture on the right is actually VLT Aries IFU image of the same object. It's a commissioning observation. It was done maybe 6 months ago. And this includes all the emission lines that you use in your intro undergraduate textbook classes or something. So H alpha, H beta, O3, O2, N2, etc. Don't push me any further, because that's about as far as I could get to say without tripping over. But what we find is that this particular object has aging in it, because you can see the aging emission lines. H alpha derived star formation is about 500 solar mass per year. Blue light you see is H alpha. So there is extended star formation in H alpha that we don't quite pick up in the infrared. And they're probably spatially displaced. AV greater than 10 is probably light. And I think mostly it's true in the parts of the new C H alpha. The average H alpha or H beta ratio is about 9. So those of you who know what that means, I hope you tell me later. Okay, and there's actually this is submitted to Nature. There's an X-ray observation which was submitted to either Nature or to the monthly notices. We also see X-ray from this source and it's X-ray binaries, data from the spectra, big enough counts. So this is becoming a very interesting new avenue of studying high-redshift galaxies, and these are almost all strictly disk rotation dominated. Okay, thank you for your patience.
Thank you.
Thank you, Min. We have time for one quick question. Anyone?
There's Atlantic talk later. I'm looking for that one.
So Ming, I really like the advice early this week. You say that whiskey really helped the throat, so I followed your advice and almost lose my voice too. So this is really not my area. This alpha rate you derive is very high. Is that just a sample selection or?
Yeah. It is selection. We want to look at the really forming factories, the galaxies that are forming most as the galaxies. But when the L-star galaxy at redshift 2 has separation rates of 100 solar mass per year. So high-redshift galaxies are not like galaxies when you go outside at night, or not here, but you go to KLS. So they are really different, and you have to have a different mindset.
Let's thank Wayne again. Thank you. And our next speaker is Daniel from ASIAA, who will talk to us about the Pulsar scintillation screens.
Yeah, I'm a bit of a fish out of water speaker in this section. I found a little bit of cosmology to work into the end of the talk, but for the most part, we're sort of focusing much more locally within the Milky Way. So I'm talking about imaging pulsar scintillation screens using Earth-based VLBI, and so to start off, I should like explain what these pulsar scintillation screens are. So the first cartoon picture that we get of what's going on is that we have signals from the pulsar. They're propagating through the ISM, and then they're being measured by our telescopes on Earth. And because they can be lensed by variations in electron density through the ISM, it can result in formation of multiple images of the pulsar on the sky. We don't resolve these images directly, so what we're really seeing is this interference pattern, which we show to this what we call the dynamic spectrum. So the intensity, the average pulse intensity as a function of time and frequency. And that's going to vary over time and frequency as the Earth, the ISM, and the Pulsar all move, and these images shift around, and we move through the interference pattern. And the one thing that was discovered, I guess, 20 years or so now, is you do the Fourier transform of dynamic spectra, they actually become a lot simpler. And you get this very nice sort of parabolic structure. And that's what tells us quite a bit about the what's going on in the ISM. So what we're looking at in this picture is that this Fourier transform, every point here represents the interference between a pair of images in the ISM. And so we'd like to sort of go back and take a look at, find those individual images. And so more mapping around into different spaces. And I think there's sort of this underlying, more fundamental object. Before you have your intensity, you have your original electric field, which we just sort of call the wave field. That's the sum of the waves from all of these images. And in that case, in that same Fourier space representation, you have this nice thin parabola, and every point here is in just one of those images on the sky. And it's got some geometric time delay, and some Doppler shift due to the relative velocities of the Earth, the Pulsar, and the ISM. And so that's a much easier space to work in. You can isolate individual images and start asking questions about where they are on the sky and what they're doing. But first we need to make our way back to that wave field. And so we need to be able to undo this convolution step. So I've got a couple, what I mentioned before, is the things that are in this conjugate wave field. And this is the picture that we're sort of working from, where you have this collection of images that sort of at some fixed distance and lying along some straight line on the sky. And that sort of very naturally forces them to lie along some parabola in the secondary wave field, which again, from the convolution, gives that parabolic structure with these inverted arclets that we were looking at earlier. And now we get to recovering the wave field. And so we want to undo that convolution, which could be difficult. Fortunately, it's just the game. Scintillometry is the game of trying to find the right space to work in. So we just apply this mapping where we just basically flatten out all the parabolas here and turn everything into a nice square. And in that case, this convolution is now just an outer product of a vector with itself. And that's something really easy to do. You can just do it with one line in Python. And you can recover sort of some really nice wave fields, some very nice thin arcs, and every point along those represents some image on the sky. And if you have multiple stations, you can do this to the dynamic spectra from every station that you have a measurement for, and start looking for phase differences between these images. And that just lets you do sort of this normal VLBI, start mapping them onto the sky. So this is just one picture that we have. So we've seen all the images lying this very straight line. There is another collection of images that sits offset. This seems to be some from an additional lens, but we're mostly focusing on this main lens. And one thing that we can also look at is we can look in this, that space, or dead space, we've made everything very square, and look for how much do these images sit offset from that main parabola in that space, which also acts as a little bit of a proxy for how offset they are from this straight line. And one thing we saw when we were looking at that is that there's these fluctuations of about a quarter of a milliarc second. But this is not the nicest way of looking at it. Ideally, we'd like to go back to VLBI to measure these, something that's a little more well understood, a little more acceptable. Unfortunately, the errors in our positions that we're getting from all of our Earth baselines are about 6 milliarc seconds, so just a little bit too large. So we want to, for our next step, use these slightly larger baselines. So we go from the next step up. We're going to start doing some Earth space baselines. And fortunately, the Radio Astronomical Telescope, a 10-meter radio dish, orbiting a highly elliptic orbit, and sometimes goes out past the moon before swinging back in. And he has been sort of combing through the archive of all of their data and looking for some, particularly for the same system we were looking at before, where we already have a good sense of how the main direction of those images lies. So we're really just interested in how it sits perpendicular to that. So this is what some of that data looks like. It's not, you see, it's not quite as pretty as what we had before, but it has the advantage of being, now we have further radii size baselines. So hopefully, this is, so the next little bit is trying to work with these, slightly less clean parabolas and using some of all the information we already know about the orientation of the screen to really narrow, zoom in on those little wiggles. This first data was really nice that we started looking at. And so this orange line is the actual baseline between Westerbork and between Arecibo for this day and Radio Astron. And this blue line is that direction that the images were lying on that we seen earlier. So this is almost perpendicular to that, which is great, because what we're interested in are those little wiggles perpendicular to this line. So we're in the process of analyzing that, and also sort of get a sense of what we can do. We're also looking at another day from the same source, where this time the spacecraft is sort of lining our baseline up, so it's much longer, but almost entirely along our line of images. So it's going to be another fun one to play with, but just sort of looking along the main direction, but that won't tell us too much about that perpendicular offset that we care about. And so that's where I was going to end this talk. So just a brief overview of what's going on in pulsar scintillometry. But then I saw it was in the cosmology section. Unfortunately, just earlier this year, we started working with some collaborators in Toronto on seeing how we could apply this to FRBs, and particularly to try to get nice distance measurements to FRBs to try to nail down an H0 measurement. And so the general idea is we're looking for sort of a double lensing situation where first you have your FRB gets microlensed by some sort of stellar mass object in an intervening galaxy, and then those two images are lensed again by this very close ISM screen. And so then we can use, these screens are AUs long, so we can use that to hopefully get us down to the microarcsecond resolutions we need to try to pinpoint the separation between these two images. And because it's a FRB, it's got a very short time structure, so it's easy to pull out the time delay between these two images. And so once you've got that separation and that time delay, you have a distance. And if you've localized your FRB to a particular galaxy, then you have a redshift, and your job is done. So that's sort of early works. If anybody's interested in hearing more, there's actually going to be a visitor here at ASIAA next week talking in much more detail about this project. Thank you.
Any questions for Daniel? On the first part, or on the cosmology part with the ISM screen? Okay, then let me ask a question. So this very last part for the ISM screen, so what do you learn from the ISM itself? So if you were to have some measurements about those microlensing events, can you turn it around and actually constrain the ISM screen itself?
We have to go a little bit the other way around. So when we make this measurement, the first thing that we actually have to do is figure out the size of this ISM screen. So in this particular step, mainly what we'd be getting is just a separation, a sort of scale between these images. I don't think this would necessarily be the best position for figuring out exactly what linear structures are, which I think is a lot more what we're interested in the earlier part with the VLBI.
So could you constrain some of the ISM microphysics? Or what exactly goes into that measurement when you say that size?
So really, all we're getting from this is just a VLBI. Basically, we're just measuring a time delay between two images. So I don't think from this we would get too much, from this particular experiment, we wouldn't get too much new information about the ISM.
Any other questions or comments? Okay, if not, then thank you very much. So our next speaker is Yun-Ting, who used to be also in Taiwan before moving to JPL.
Okay, so hello everyone. So I'm Yun-Ting. I'm now a postdoc at JPL at Caltech. And today I want to tell you a bit about some of our recent work on cosmology from the diffuse emission in the extragalactic background light. Okay, so what is the extragalactic background light, the EBL? The EBL is basically the integrated light coming from everything along the left side across all the redshift in our universe. Okay. And here's a measurement of the EBL starting from UV to about 5 infrared wavelengths. And in this EBL spectrum, the shorter wavelength part, about UV to about infrared, is coming from all kinds of stellar synthesis processing of universe. And the fine infrared emission is mostly coming from the dust that absorbs some of the stellar emission and we need a thermal radiation of fine infrared. Okay. And now let's take a closer look at this EBL on the near infrared part. So it's around 1 micron. So as you can see, there are a lot of data points in this near infrared EBL measurements, and they have very large scale between each other. And this is because they are taken with very different kind of method. So the first way we can constrain the near infrared EBL is using galaxy counts, which means you take a very deep integration of the sky, and then you try to resolve all the galaxies you can, and you count the total amount of photons coming from all these galaxies. So then you can get a lower bound constraint on the EBL because you cannot capture light from the sources below the detection limit. Okay. And then the other way to constrain the EBL is, of course, you directly measure what's the total intensity, total emission coming from everything on the sky. So this is called the absolute photometry. And those data points in the green box are coming from the absolute photometry measurements. Okay. So one big question in this near infrared EBL field is that if you look at those absolute photometry measurements, they are a few times higher than the galaxy counts. So that means in our near infrared sky, there are a lot of photons is actually coming from either very faint or very diffuse sources that we cannot capture with the individual detections. So what are these very faint and diffuse components on the sky? Okay. And there are a lot of different possible theories. So first, it could be the sources from the Apple organization. So these first galaxies are very faint, we cannot detect them individually. Or you have some very faint low-energy galaxies that is below the detection limit, even with the very, very deep integration. And another theory called extragalactic light coming from stars that is tidally stripping away from their host galaxies during the merger. So these stars become a very diffuse envelope around the galaxies, but you will miss these kind of photons when you just detect the central galaxies. Okay. And there are also some more exotic possibilities, like the signal from the direct black hole coming from very high redshift, like during the dark ages. Or another possibility is called the decay signal of the axion-like particle, which is one of the dark energy. Okay, so I hope this gives you some motivation of that there are a lot of very interesting science, either cosmology or astrophysics, we can explore with this game-free background, and there's still a lot of photons out there we don't know where they come from. And luckily, in the next couple of years, we'll have a much better measurement on this game-free EDO, thanks to this next generation cosmological survey like Euclid, Roman, and SPHEREx. Okay, and now I'll take a closer look at SPHEREx. Okay, so here's a brief introduction of SPHEREx, and I'll just briefly go through it because the next talk, Olivier, will give you a more detailed introduction about this mission. So SPHEREx is a NASA satellite mission that will be launched in 2 years, 2025, and it will be the first all-sky infrared spectral survey covering 0.755 micron, and with about 100 spectral channels. And then these are the 4 main science targets for SPHEREx. So one is to do cosmology, to map a bunch of galaxies on the sky to trace the local structure and construct the primordial functionality. And the second one is exactly to study the EDO, and I'll talk about that in detail later. And the other one is doing more galactic science to look for the water signature in the ice and also will provide an all-sky spectral data, images, and the catalogs. Okay, so how can we do with SPHEREx for this EDO science? So here's a model of the extragalactic background coming from all the galaxies, from redshift 0 to redshift 10. Okay, so if you just take the SPHEREx data and you add okay, what's the intensity at different frequencies, then you will get the black line on the top, which is the integrated signal coming from all the redshift from all the sources. Okay. But if you can break down this signal into the contribution from different redshifts, then you can see there are a lot more features in these different SEDs. You have the different shape of the continuum, you have some spectral lines. But all this information is degenerate if you can only measure the total intensity. Okay. And the way you can try to try this degeneracy is using cross correlation. So the idea is that okay, you can take some galaxy catalog and cross correlate with the SPHEREx images from different color. Then for each of these cross correlation, you can extract the EDO emission just coming from that redshift. So then you can get the data point on one of those color lines. And then you do all this cross correlation, we can reconstruct the EDO signal from different redshifts. And then we wrote this forecast paper with Tzu-Ching earlier. And we have a pretty promising forecast according to our model. So yeah, here's some of our results. So at the very low redshift, about redshift 1, we can do cross correlation with, for example, the DESI spectroscopy catalog, and then we can get about an SMR of the 20 to 30 on the EDO spectrum. And even for the very high redshift, say at redshift 6, that is almost a ionization redshift. And if you take the SPHEREx data, cross-correlate with the LSST photometric galaxies, then you can still get a pretty good detection. Okay, so this will be a very powerful tool to study a lot of things like the galaxy evolution and the star formation rate evolution, if we can get this kind of measurement across all redshifts. Okay, so this is great, but one downside of this is that we need an external catalog to do this cross correlation, and it is not always easy to find a very good source of external galaxy catalog to do this. Okay, so another thing we have been developing recently is to do this EDO inference, but without any external information. You directly take the SPHEREx data and can do the inference. Okay, and so here's the idea. So let's say our lab is our SPHEREx data. So you have these intensity maps from different frequencies, and the signal here is coming from everything across our observing dipole and from sources from all the redshifts. And now let's say we can describe the signal field in terms of different type of galaxies. So for example, I have these blue, red, and green galaxies. And for each of these type of galaxies, I have the specific SED, like it could be the old galaxies or the star-forming galaxies or quasars. And then you also have some redshift distribution in terms of their luminosity density as a function of redshift. And now if we can do this, okay. And now all these galaxies is tracing the underlying density field. Okay. So then our signal looks like this. So you have your intensity is the integration of all the sources across redshift and all types of sources with their SED and their redshift abundance. And this is the bias tracer of the underlying density field, delta M. Okay. And now what we're going to do is to do this in the Pulse spectrum space. So I can take the cross-Pulse spectrum between two different frequency maps in SPHERex. So then the Pulse spectrum will be looked like this. So this CL is a function of frequency lambda and lambda plot. And it also has some components of the SED and the redshift abundance, and because it's tracing the underlying density field, so I have the Pulse spectrum of the matter density field. And then we also have some noise in the data. Okay, so then the thing we're doing here is you take the SPHERex data and then you do all these different cross correlations to get a bunch of cross-Pulse spectra. And then we can use this to infer the underlying information, both the astrophysical information about the SED from different type of source and their redshift distributions, and also the cosmological information, so the Pulse spectrum of the underlying density field. And at the same time, we can also infer the noise property in the image. Okay, so that's the basic idea of our work. And if you want to learn more details, then we already have a paper on archive here. And also I want to emphasize that, so this is a very different way to do cosmology, because traditionally, you take the galaxy survey, you first detect the sources, and then you measure the redshift either with the photometric or the spectroscopic redshift. But here we just directly take all the photons we measure in the map and directly do this inference from everything without making a lot of assumptions. So this is a more data-driven way to infer information from the data. Okay, and just to give you an idea of how this works on the SPHERex data, so we did a forecast on how well we can constrain the Pulse spectra, P of K, using our method. And as you can see, this is the SMR on the Pulse spectra per beam, and we can get a pretty high sensitivity measurement if we have the SPHERex data. Okay, so I'll leave my summary here, and I'm happy to take more questions.
Thank you, Yun-Ting. So, any questions for her about this SPHERex multiversal?
One of the analyses you're doing is SED getting a statistical way of accounting for the light. Of course, your model is only going to be as good as the model you're allowed to have. How much confidence do you have that you have the sufficient SED libraries to come up with a robust tensor? What kind of uncertainty can you assign?
Okay, so we actually don't use any library, so we directly try to figure out the SED from the data. And the way we did this is we pre-assign, say, okay, we want to fit, say, 10 type of SEDs, and then we directly discover that from data. So it's a bit like doing PCA directly from the data. And to directly answer your question, so there are people like look at the doing PCA analysis of all kinds of galaxy SEDs, and they found that you don't really need too many components for to really describe the variation of the galaxy SEDs. So we think we don't need too much SED components for this.
Any other questions? So what is the external catalogs that you are using?
So we consider a lot of basically all the spectroscopy and photometric catalog we can possibly access, so including SPSS, DESI, and also Cheng itself can also produce a Galaxy catalog. So we can also do this internal extragalactic, and also in the future we'll have nuclear Roman, and for the photometric one we also have the LSSE, and Roman will also have the photometric data.
So is that, will that allow you to get a robust estimate for what is in the aggregated signal? Because everything is aggregated, it's an aggregated measurement. Also, I mentioned there's still some degeneracy left, depending on what catalogs are, what the catalogs are.
So the idea here is if you look at the large-scale correlation between catalog and image, then you are pulling out just the total intensity, but not really depends on the specific catalog you are postulating, because they are both traces of the underlying structures.
Any last question? Okay, good. Thank you very much. So we are now moving ahead to the last talk of the session, which is the recorded talk by Sherry Suyu, who unfortunately wasn't able to make the trip in person. So she has sent a recorded talk. Then after that, we will go back to Tzu-Ching's and Olivier's talk.
Hi everyone. It's sad that I cannot be there in person to celebrate with Paul and me during the special occasion, so I recorded this presentation to join you virtually. I'm Sherry Suyu. I was an assistant research fellow at ASIAA, and I'm now a visiting scholar at ASIAA while being based in Munich as an associate fellow. In the context of the conference on probing the universe at higher resolution, I'm happy to share with you how strong gravitational lensing is nature's cosmic telescope to probe the universe. In this animation, we will see a strongly lensed quasar system. So on the left, we have a quasar, and we are here on Earth on the right. Light rays strongly emanate from the quasar, and if there is a massive galaxy between the quasar and us on Earth, it will reflect the light rays from the quasar such that we can see multiple images of the quasar around the foreground lens galaxy. On the top right, we have an example of a lens quasar system observed with the Hubble Space Telescope. Such a system is not only beautiful, but it is a powerful probe of cosmology and astrophysics. For example, we can use such systems to probe the evolution of the universe by measuring distances to these objects. We can also measure the mass distribution of the foreground lens galaxy, disentangle dark matter and baryons to study the galaxy structure and galaxy evolution. We can use these systems also to study both the black holes in the lens galaxy and also the black holes that power the quasars, which is important for understanding the co-evolution of supermassive black holes and their spheroids. In the final example, we can also use such systems to explore how supernovae explode. In this presentation, I will focus mostly on black holes and cosmology. First, black holes. On this slide, you can see ALMA's first high-resolution image of a strong lens system. This beautiful Einstein ring was released by ALMA Partnership and is called SVP81. We compare to previous observations of SMA in the red contours and also the Hubble Space Telescope imaging in grayscale. You can see that the ALMA high-resolution imaging really gives us a high angular resolution view. And when this beautiful image came out, it was Paul who encouraged several of us at ASIAA to make use of this new data set for scientific studies. In particular, Kenneth Wong, who was at Yakuza ASIAA, Satoshi Matsushita, and I used this system to try to probe the black hole in the foreground lens galaxy, which does not appear in the sub-millimeter observation, or which you can see in the near-infrared observation. Lensing theory predicts that there should be a demagnetized central image of the lens background source near the center of the foreground lens. And the brightness of the central image is sensitive to the mass of the black hole and also core radius of the lens galaxy. When we looked into the CO line map, we actually do not detect this central image, and this places an upper flux limit on the central image that translates into a lower mass limit on the black hole mass in units of solar masses, where we find log and black hole has to be greater than 8.5 for a galaxy core radius of 0.15 arc seconds that was measured from the Hubble Space Telescope imaging. Now, these lens systems not only allow us to study black holes, we can also study cosmology using the time delays. This was a snapshot of the animation that I showed you, where we can see the multiple light rays from the quasars reaching us on Earth. And because the different quasar images take different light paths, the time it takes for the light to reach us with the different images will be different. Longer light path will take a longer time. And also there's a gravitational delay of the lens. Since the quasar is a variable source, we can see the quasar light flickering, and we will see the flickering pattern manifest in each of the multiple images, but at different times. And by monitoring such systems, we can measure the time delay between the multiple images. This time delay can then be translated to a distance by modeling the mass distribution of the foreground lens. And once we measure this absolute distance to the lens system, this allows us to measure the expansion history of the universe, particularly the expansion rate. This is what my collaborators and I have done in the Holy Cow project, which stands for H0 lenses in Cosmos Wellspring, where H0 stands for the Hubble constant that sets the expansion rate of the universe. This is a project that was initiated during my time at ASIAA, and our goal was to measure the distances to these 5 lens quasar systems such that we can constrain the Hubble constant with 3.5% precision, which is important to address the current tension in the H0 measurements between the early and the late universe. Here was the final result from the Holy Cow project, where we have measured the distances to actually 6 lens quasar systems. So shown here is the probability distribution of H0 for each of the 6 lenses in 6 different colors. And you can see that the probability distributions overlap, meaning that these measurements from the different lenses are statistically consistent with each other. So we proceeded to then combine the constraints from all 6 lens quasars to get a joint constraint on H0 shown in black. And this is an H0 precision with 2.4% in black lambda CDM cosmology. This is a standard cosmological model where the universe is spatially flat, contains dark energy described by the cosmological constant lambda, and called dark matter CDM. So this is the result that was led by Ken, who was at ASIAA and is now a professor at Tokyo University. One of the dominant sources of uncertainty to measure the distance and subsequently the Hubble constant is the uncertainties associated with the modeling of the lens mass distribution. In this respect, spatially held kinematics of the foreground lens galaxy are key to breaking mass model degeneracies and to measure the lensing distances. And this is where JWST, the James Webb Space Telescope, will be revolutionary. So on the left, I show you an image. So this is from an integral field unit observed from the ground at Keck Observatory using the KCWI instrument. So this is a lens quasar system where you can see the multiple quasar images. It's kind of blurry because of the Earth atmosphere, and it's quite hard to extract the kinematics of the lens from the ground. And we just the imaging, the spectroscopy, also integral field unit IFU, near spec on board of the James Webb Space Telescope, and this is the same image of this is the image of the same system where you can see clearly the multiple images of the quasar, and you can actually see the foreground length galaxy very clearly, and it's from IFU data set that we expect that we can extract spatial result kinematic map as shown here. This is a simulated one showing the velocities of the stars in the foreground galaxy, and from this kinematic map we can then do a joint lensing and dynamical analysis of this lens system in order to infer lensing distances and thus the H0. Now, when the method of time-delay cosmology was first proposed by Rest in 1964, he had envisioned actually lens supernova rather than lens quasars. But lens supernova are very rare, and therefore this method was actually realized with the more abundant lens quasars. Nonetheless, in just the past few years, we are seeing the very first strongly lensed supernova, and in particular, earlier this year was an exciting event of a lens supernova that was caught by the James Webb Space Telescope by the Pearls team. So on the left is a JWST imaging of a galaxy cluster. So these white blobs you see, these are galaxies that are gravitation bound into a galaxy cluster. So you see two clumps here. And then you see these orange big arcs. These are background galaxies that has been strongly lensed. So shown here is a background galaxy lensed into 3 images. And here's a zoom on the right where you can see the 3 images. And if you look closely, there's actually point sources, 3 point sources here labeled 2A, 2B, 2C. This is a supernova that is appearing in this host galaxy, and as a result, it's being strongly lensed into the 3 images that we see. So our team here in Munich is working closely with both the Pearls team and also the LensWatch collaboration in order to use this system to measure the time delays and also model the cluster mass distribution in order to infer the distance and measure the Hubble constant. So given that lens supernova has become a reality, our research team in Munich has started a new research program which we call Holy Smokes. That stands for Highly Optimized Lensing Investigations of Supernovae, Microlensing Objects, and Kinematics of Ellipticals and Spirals. This is a program that is funded by the European Research Council. And our program has 2 main goals. First is to measure the Hubble constant through this time delay method that I've just described. And then the second goal is actually to constrain the progenitor of type 1a supernova, which is a powerful cosmological probe, but we don't quite know yet what the progenitor system is. So there's 2 caustic scenarios shown here. On the left, we have a single degenerate system where we have a white dwarf accreting material from the non-degenerate companion, and as the white dwarf approaches the Chandra-Sekhar limit, it explodes. Or you can have a double degenerate scenario where you have 2 white dwarfs merging, or it could be more complex mechanisms such as delayed detonation or double detonation. And to really decipher what the progenitors of type 1a supernova is, what really helps is early phase observations shortly after explosion. So these are precisely the kind of observations that has been very difficult to acquire, because usually by the time you detect a supernova, you try to arrange for follow-up, especially in the rest frame UV wavelength. By the time you've arranged follow-up, you've already missed the first days after explosion. And this is where strong lensing with the time delays can really help you, because what we aim to do is we try to find a lens supernova based on the first appearing image, and then we can use our mass models to predict when the next image is going to happen. And basically this time delay between the first and second image is the order of days or weeks, and this gives us time to arrange for follow-up to target this spectra in the Rush-Ring UV to study the progenitor stuff, type 1a. In order to achieve our two goals, we have multiple components in our program. On the top left, you can see that we're developing new methods to find these lenses. That's essentially the first step to first detect these systems. And then we have also strategized ways to follow up these systems. We are developing new methods to measure the time delays between the multiple supernova images, both based on photometry, so light curves, and also through spectroscopy. And finally, we are also developing new methods to model the lens systems very rapidly in order to enable the follow-up of lens supernova. If you're interested in more details, you can find more information on our website at www.holysmokes.org. So to summarize, strong gravitation is a powerful probe of cosmology and astrophysics. The ALMA DP81 places a low on the black hole mass in the lens galaxy. The lens transients with time delays allow us to measure distances to the lens system and therefore the Hubble constant. And we have initiated a new program, Holy Smokes, on lens supernova to study cosmology and supernova physics. Thank you very much for listening, and I wish you a wonderful conference.
Questions for Sherry? Write to her directly, please, or you can send me your questions and I will pass them on to her. So, we are moving back to SPHEREx with Olivier. So he'll give us an update on the SPHEREx mission and also tell us something about extinction mass.
Thank you, Patrick, and thank you everyone, and thank you the organizer for giving me the opportunity to speak. So I'm very happy to speak today. So if you don't know me, so I'm Olivier Doré, and I work at JPL and Caltech, but I'm also a visiting scholar at ASIAA. And today in my talk we have two parts. So the first part will be detailing ongoing work with Yun-Ting and Tzu-Ching regarding the difficulties of mapping dust extinctions from the galaxy from the sky, and why it's difficult for them. And the second part will be to give you a brief update on hopefully to create some excitement about SPHEREx, who is going to launch in less than 2 years. Okay. So mapping dust extinction is each one. So why do we do that? Why is it important? As you all know, galactic dust will extinct distant galaxies. And if you try to measure in 2D or 3D the detailed clustering of galaxies, the detailed distribution of galaxy, you need to take into account, you need to model, you need to remove the effect of dust, which will introduce some kind of quantization, modulation of your galaxy field, which will lead to a bias. So it's something very important for cosmologists. It has been done, it has been done in different ways in the past. And that was one of the most quoted papers in astrophysics, the Shade-off Invariant Davis maps, which we use far-infrared emission, right? The SLP, famous SLP dust map. So what we are trying to do is actually use H1, which is a map of neutral hydrogen, to map dust extinction. So why do we use H1? First, H1, as you can see this plot, when you see extinction as a function of H1 column density, H1 is at low column density is very linearly correlated with dust extinction. So if you know H1, you can predict extinction fairly reliably. And you also notice that when at higher the column density is not true. Right? But at least in this regime, you can do that. And one very important virtue of using H1 to trace dust extinction is the fact that H1 is not contaminated by the infrared emission from distant galaxies. So the cosmic infrared background that will appear in far-infrared maps or near-infrared maps, as Yun-Ting said. So the problem for cosmology is that if you use extinction map which is built on far-infrared emission, you will also overcorrect or undercorrect somehow because you have in your map, you have the extinction, you have the emission coming from the galaxies you are trying to measure the clustering from. So that's an important challenge. And so, does it work? We are not the first one to do that, so it works, but to some extent. And the way to validate that is we need to compare, you can build even at the scale in different regions, you build a model of the extinction given H1, and you compare it to what Planck saw in the 5 Farad, and you see it works, it's really reduced substantially, so it's hard to see from this plot, but the key point that you reduce substantially the emission in the 5 Farad, but you also see large-scale residuals. And it's understanding the challenge. And the large-scale residual is typically what you try to measure. Large-scale is typically what you try to measure with in cosmology. So we try to improve on this work, and we use a new approach. And it works to some extent, but so the new approach is to use a better algorithm, a more sophisticated algorithm, which is an unsupervised clustering algorithm, to identify someone automatically in a pseudo-phase space, various phases of the ISM. So we apply a clustering algorithm in angular velocity space so that to trace as much as possible various phases of the ISM. And then for each of these regions, we then build a model using the relation between H1 and 5 Farad. So that you see here different regions. You can see that this region could be a very broad velocity, very large velocity beams, but very few angular structure, very little angular structure, or you can have very narrow velocity beams and large angular structures. And this is something that came out of the algorithm we use. And so does it work? Yes, it works much better than the previous approach because it makes sense because we work closer to the phase of the ISM, so we have more sophisticated models in order of extinction, but we still see large-scale residuals. And this is something we have been puzzling over for the last year or so. Yun-Ting can really tell me more about it. I'm finishing a paper on this, which is a substantial paper, and there's a lot of questions. So why doesn't it work better? It's actually an open question. We have not solved this issue yet. It's a kind of a tricky, and we're a little bit puzzled, and I think we're stuck a little bit. So if you want to be interested, you want to think about that, your input will be welcome. So can it be dust to gas ratio variations? We expect dust to gas variations throughout the sky. Yes, but we don't find evidence for that through use of the data sets. Can it be dust temperature variation? We know that the dust temperature will vary throughout the sky. Yes, but it's not consistent with what we know, independently from dust temperature variation, or can it be other hypotheses like a non-negligible H2 fraction, which will be traced by CO, can be CIP contamination again, etc. So we asked a lot of questions, we have a lot of discussion in this paper, but we don't have a clear answer yet. So please go talk to Yun-Ting if you're interested. And this is work led by Yun-Ting and Tzu-Ching and run on SKD all at JP. So that's the first part of my talk. And the second part will be really to give you an update about the SPHEREx mission. Okay. So SPHEREx was selected as the next NASA MEDEX mission, which is a completed class of mission, which is the same class of mission as the WMAP, TESS, or the WISE missions. And there are typically 1 or 2 predicates. And SPHEREx was designed to address 3 key scientific questions. The first one is how did the universe begin? And the way we do that is by measuring the clustering galaxies on a larger scale to try to constrain the physics of inflation. That's really our number 1 of 3 goals. The second goal is to look at the origin of galaxies. And so we do that by mapping very reliably the EPL light, the diffuse near-infrared calculation, and from that we want to tease out the signature from ionization. And that's something Yun-Ting just discussed. And our third scientific theme is really what are the conditions for life outside the solar system. And we do that by looking at the spectra of absorption feature in stellar spectra throughout the galaxy. That's all. And so to answer this question, we start to probe the origin of the universe, galaxies, and life. But to answer this question, we will really do so by constructing the first all-sky near-infrared spectral survey. So this data set, that's one thing you should remember about SPHEREx, that's going to be this data set, which is really a first all-sky near-infrared spectral survey. And so what it means, and I think that's really a key takeaway from this talk, the data set that we release very quickly after we take it, is the fact for every single pixel of the sky, every 6.2 single pixel of the sky, we will have a low resolution near-infrared spectrum. So between 35 and 41, between 0.75 micron and 3.8 micron, and a slightly higher resolution between 110 and 130 R, between 3.8 and 5 microns. And again, so for every pixel of the sky, every 6.2 pixel of the sky, we will have a spectrum. You can see that we are discussing here low resolution near-infrared spectroscopy. You can think of it as fine band photometry. And if you think of it this way, you can think of the SPHEREx dataset as being 102 fine band, all scan map, 6.2 arc-second resolution. So that's the dataset we want to produce. Of course, it's not enough to specify the wavelength coverage, you want to specify the depth. And what you see here is the depth as spectral magnitude. You see the wavelength is 0.75 micron. Each black points here correspond to the sensitivity, the forecasted sensitivity throughout the sky. So you have 102 elements here. The lower part corresponds to the most conservative estimate, and the upper part corresponds to the most optimistic estimate. And here you see that that's for the whole sky, and we have two deep fields which are near the north and south ecliptic pole, each is about 100 square degrees, so we are about 2 magnitude deeper over in this deep fields. As a reference, you can see here the WISE 1 and WISE 2 all sky depth, and so you can see that you can think of it that we have the same depth as Y for each frequency element. So you can think of this data set as giving you a spectra for every single WISE source state, right? So it's going to be a very unique data set, very interesting data set, very new data set. And so the important part of this plot, that's the plot we generated in 2018 for the proposal before we got selected. And now we have built instruments which is being tested in the lab right now, and I'll show you pictures of that. And our measured performances are actually very close to this optimistic level. So this is very satisfying. So we are really very close to this limit here. That's all I can say. Okay, so why do we do that? What do we expect to see with SPHEREx? So we expect more than 1 billion galaxies, so with spectra. And with this spectra, we have high medium redshift accuracy, which is redshift accuracy of about 10% for us for more than 100 million galaxies. We have more than 10 million galaxies with high redshift accuracy, which is the accuracy you need to measure VLBI, that's about 0.3%, in sigma 0 Z. We expect more than 25,000 clusters, in fact more than 100,000 clusters with redshift. Of course, many stars spectra, about 100 million stars. We have all sky surveys, so we are of course naturally very good at finding rare objects. We expect about 10,000 dust forming stars, about 400 brown stars, about 4,000 galactic stars. We are also very good at finding distant quasars, because they're actually pretty bright in the infrared. So for example, we see more than 1 million quasars, and if there are quasars, greater than redshift 7, we know 3 of them right now. They're actually very bright in the infrared, so we should see them, and we should see the random emission and measure their masses. Okay. And it's going to be also very exciting for solar system objects. Also, we get a spectra for every known asteroid or comet, which is very important for this. Okay, so that's how SPHEREx looks like. Just a quick overview. So it's 2 meter high, so just up to my height, and it's a small telescope, so 20 centimeters, but a very wide field of view, right? So it's very about more than 38 square degree field of view. So it's a very fast optic. It's a survey instrument. So it's 20 centimeters. It's passive cooling. And again, I show on the key feature here. You see the detector. This is 3 TMN mirrors. You see mirror here, and the detectors are here. And the key feature, I don't have time to explain that, but the key feature is that we measure spectroscopy by having what we call linearly variable filters, which are fixed in front of the detectors, and we just step the spacecraft across the sky to measure multiple exposure, and we reconstruct the spectra in post-processing. So that's how the spacecraft looked in the proposal during design, and that's where we are now. So what you see here, this is a time-lapse movie done a couple of weeks ago in the basement of Kahil. You see we are busy here building the telescope. See the telescope is fully built, instruments are here, the V grooves here for passive cooling, and here you see a large vacuum chamber where we do a thermal vacuum test delivered by Classic, actually, our partners at Classic, and we are testing it many times on measuring the property. That's the beautiful thing about SPHEREx, that it's a small payload, it's a small instrument, so we can actually build a full instrument, put it in this chamber, test it, and measure its property, which is very, very unique and very satisfying, very reassuring, of course. So that's how it looks. And again, that's interesting also is the fact that that's the basement of Caltech, so it's a university-sized project. It's not a big like a JPL. So we are busy, and this is still ongoing actually, we are still doing such a test as of today. And seriously, this is a window to project light inside to do the calibration. It's a sapphire window, a very thick sapphire window, and with a gold plating, which gives great opportunities for self. You see here our instrument coming from this reflection. Okay, so another picture, because it's pretty, and that's also the vibe test, vibration test. We have to simulate, to test the spacecraft, we have to simulate the launch. So there's a vibration test where we put this payload, the full instrument already built, with already focused on a big vibration table, and that's what done at JPL 3 weeks ago, and it passed successfully. And that's very impressive test, it's checked out about really high frequency, about 40 G lateral, so it's very violent, but the instrument is very solid, and it passed with flying colors. So we see in focus after, which is good. And that's it. So before concluding, I really want to also take this opportunity to thank Paul for all the advice on illuminating support in many different ways throughout the year. So I'm very grateful for that, and I'm looking forward to more advices. And so I'll just give you a summary. SPHEREx will create a fourth all-sky infrared spectroscopic survey. I didn't have time to detail, but all the data will be quickly released. So because we want the community to engage with our data set. So we expect many discoveries with data set, and so we want the discoveries to come from the community. SPHEREx will have 3 main goals. Currently we're on schedule for launch in early 2025. Thank you very much.
Thank you very much. Questions for Olivier?
Hey Olivier, great talk. So can you explain a little bit more about the filter system? Are all of the colors obtained simultaneously, or are you stepping through the channels at different times?
You're stepping through the channel at different times. So actually I removed a nice animation turned out, but I removed it from this package. I'll show you. So but the way it works is that we have our focal plane, we have our detectors, and we have so this linear event feature, which is a fixed features, and each row is very linearly with position, and so each row of the detectors, infrared detectors, we see a slightly different color. So when you take one exposure, which is just like imaging, you will see different wavelengths across the sky. And so what you do is that we have designed a survey strategy where you will step the focal plane across the sky, and then in post-processing you reconstruct the spectra for every point of the sky. So that's the virtue of that, is that it's very, there is no moving part. It's like doing imaging, it's not really doing spectroscopy, so it's very simple to operate, very robust, very much simpler to analyze. Yeah.
But the time delay between the different colors is...
Yes, so it's fine for galaxies, most of them are not variable, so that's fine. But if you are actually time variable objects, then we have to take that into account, right? And for example, for solar system objects, whether you have the asteroids are tumbling, so you have to take that into account in your modeling. That's right. If you want to study, let's say, quasars or system time varying, then you have to take that into account. It's a funny time color observation window. Yeah.
Interesting.
Yeah.
I wish you had this for me 6 years ago. It saved me about 4 years of work. But we'll have to live with that. 6 arcsecond pixel is still kind of big for galaxy evolution work.
Right.
But maybe you've done some, for the depth that you want to reach, I guess maybe it's not so much a problem. What kind of confusion do you expect?
No, that's a very good question. It's an important question. I think the key point here is that SPHEREx is not a discovery. We cannot, for the galaxy survey, we already know all the galaxies we will take a spectra from. So because, and so what we do is that we use optical survey like LSST or DS, and we use LSST, but DS or Pulsar or legacy surveys, which tell you at higher angular resolution and deeper, which tell you in which pixel how many sources we have, if it's isolated or not. If there are multiple sources, more than 2, we cannot separate and we discard the galaxies. But for isolated sources, then we get a spectrum. So But for sources, for example, which are not in optical service or 100 nanometer, then we cannot say whether there is actually single or multiple sources. So that's a big, so we simulated that extensively. But the key thing about SPHERex is because of this resolution issue, we are not a galaxy discovery machine. We measure the spectra of non-galaxies. Yeah.
Okay, thanks a lot. So any more questions, please get to Olivier during the coffee break. Thank you. And our next speaker is Tzu-Ching, who was also on the faculty here at the ASIAA until some years ago.
I'm Suyu. As Patrick mentioned, I was assistant research fellow here until a few years ago, and before that, I was actually joined Pulsar also here, working with VLBI as ASIAA. So I actually was basically recruited by Paul over the years, and Paul has been a very wonderful mentor to me. So really, thank you so much for that, and thank you for all the support. Apologize for my voice. Sorry. As we felt ill unfortunately last week. So I guess before I run out of time, I'd like to share a quick story about Paul. So that's okay. So I guess a few years ago, Paul asked me to help with a fundraising opportunity for the GOT actually. To the Delta Electronics, as you know. And then, so the angle was that we would perhaps put a CMB-like experiment on the GOT, and we were looking for the support from Delta Electronics. And so I was helping to put together a poster, basically for a flyer for people to read. And so, but then, Paul asked me to tag along to the event, so I went without any preparation, but on the spot, Paul actually asked me to make the pitch on the spot. So I was actually not prepared at all, and it has to be in Chinese, of course. And for those of you who know my Chinese sucks, and my scientific speech in Chinese is definitely worse than Paul's. So that was a very daring move from Paul, and we didn't get funding. So sorry. So that was a very interesting lesson for me. And later on, I asked Paul why did he do that, and his response was actually I was very surprised because he said he realized the Delta Corporation, the people at the Delta they didn't think I was a scientist. I was just going there to help out with the event. So Paul wanted to show that we have to. Paul felt it was not right, and basically just asked me to make a pitch on the spot. So I guess in retrospect I should have been more prepared. So that one's on me. But then I guess it really goes out. It really says a lot about Paul. Like Paul is definitely a visionary, and then he really works tirelessly to get the vision done. And then, but most of all, he's super supportive of the people that work with him. So thank you for that. Yeah. Okay, so I guess I'm going to back to the talk. I'm going to talk about light intensity mapping, and this is actually again with a lot of support from Paul, and we're working with people here, as you know. So just very quickly, want to say that currently within the observational cosmology, there are two main pillars for observational cosmology. I think this is probably fair to say that one is the cosmic microwave background, and the other one is the Galaxy Redshift survey. And what I'm trying to discuss today is called light intensity mapping, which we think is basically a hybrid of the two techniques. We use the cosmic microwave background approach to map the large structure, much like what the Galaxy Redshift survey would do. And as a result, this is basically we try to map the diffuse emission of from galaxies without resolving them. So this actually allows us to probe a very significant fraction of the universe in a more economical way, and allowing us to basically probe this vast cosmological volume into the current, the CMB, where the CMB emitted from 13.8 years ago to what the galaxy surveys are probing, which are mostly the late-time universe. So like this mapping, we would like to think that it offers some great opportunities for us to basically map out every photon available in the universe, as I think you just mentioned. So yeah, basically I just said that what we basically doing is just to use to measure the diffuse emission coming from galaxies, but instead of the EBO emission that you mentioned, which is a continual emission, we're using a spectral line from galaxies as a tracer, and therefore we can actually map out the three-dimensional volume of the universe effectively. So actually there are a lot of experiments going on in the field, and actually one of the first, I think, effort is basically our work using the Greenland telescope, using the 21 centimeter emission line as a tracer. I did work with Whaley and also with Yun-Ting here, and then also that's in the radio, and also in the sub-millimeter time is also one of the first experiments using the C2, which is singly ionized carbon, and CO to trace the arterial structure. And those experiments, we were basically very lucky to have Paul support us to do all these initial experiments. And now I think the field has actually grown very much since then, and it's actually moving at a very fast pace. And this is a status report in 2017. I think the number of experiments have basically doubled. But shown here is basically the angular resolution and the survey size probed by these experiments as a function of redshift. So we can see that this is actually a pretty significant fraction that's being mapped by these experiments. I think today I'll be focusing on discussing the TIME experiments, which basically funded by ASIAA with participants from many of us and led by Charter here. And then also Yun-Ting, who spoke earlier, is also part of the TIME collaboration. So TIME is actually, I'm just going directly into what TIME is. So you can see that this is the TIME instruments, which is the TIME CloudSat being lifted into the 12-meter Alma prototype telescope at Cape Peak. This is one the picture we have when we were doing the engineering run back in 2019, 2020 pre-COVID. So the CloudSat is actually a four-stage. It's a four-stage CloudSat. The TIME will be operating at 250 millikelvin. And this is the TES bolometers. This is one of the modules. It's showing the spatial direction and the spectral direction. And this is the spectrometer, the gradient spectrometer that's been built by ASIAA. And you can see this is one of them for visualization. And then the instrument basically is pulled at 250 millikelvin and allowing us to cover the frequency range of 200 to 300 gigahertz at a low spectral resolution about from 100 or so. And this basically allows us to access the single ionized carbon at the high redshift between 6 and 7, sorry, actually much higher, like 6 to 9 or so. And we'll be actually doing a nominal survey, a grand scan survey of 1 degree by 0.4 a minute, just due to sensitivity limits. And then the science run will start later this year, so mostly due to COVID delays. And we have actually secured 100 hours of winter time at the Cape Peak around to do the survey. But there's a proposal for time to be moved to the LCT telescope, which is formerly the CSO, as you probably know, and that's been moved to Chile. Normally, so schematically, this is what the cosmological volume that time will probe, even with a small line scan, will be able to access a very large cosmological volume from redshift 0 through this CO ladders and also with the C2 emission. And so, but as you know, so I won't have time to talk about it, but then actually the CO themselves could be a signal for time, and they are also a line interloper to the C2 signal high redshift. And there are multiple techniques that we're trying to disentangle these two components, and if you're interested, you could talk to Yun-Ting later on as well. So with such a round scale survey, we are hoping, what we're hoping to measure first is a statistical measurement of C2. Basically, seeing the two-point Gaussian function or the also pulse spectra as a function of here is shown as an amplitude, and the wave number taken, which is the inverse of spatial scales or in 3 dimensions. And the green line is probably expected to measure at redshift 6, and the red one is probably expected to measure at redshift 7-ish, both of which will have expect to have a signal to noise about 10 or so. And then we'll also be able to see the post-correlation of multiple CO ladders at low redshift. So with such a measurement, we can basically infer the abundance of C2 at redshift 6 and 7 or so, and then within the model framework, we can then turn that C2 abundance into the ionized photon basically budget, and then we can use that to constrain the Snell emission rate density high redshift. And then further, we can, within this, the model framework, will further assume that we further assume or model the Galaxy speed fraction, then we can basically use the measured C2 pulse spectra to infer the realization history. So what is shown here, what is shown here is a neutral fraction as a function of redshift, and then you can see the time constraint will be basically this red band. So this will be basically an alternative approach to measure the high redshift universe, comparing to individual galaxy sort of measurements of the neutral fraction, and also complementary to the 29cm field, basically measuring the neutral fraction. So we're hoping that we'll be able to make such an inference with time in a few years. So very quickly, I just mentioned SPHERex. I think also Olivier and Yun-Ting has talked about it. So basically, so besides the EVO measurement or the Galaxy investigation or the attendant investigation, SPHERex will actually be a great light intensity mapper. And so within the wavelength coverage, we'll be able to measure multiple lines over this redshift range. So and then so there we have done a lot of work trying to characterize exactly what we can learn from such lines, and also how to work with the line interloper questions. So this is a light cone shown work by Tzu-Ching Chang, showing what the SPHERex could possibly see from the deep field, which is about 100 square degrees. And with such kind of measurement, we could potentially, one of the applications to measure the acoustic oscillation using H-alpha emission from SPHERex will like even gamma alpha, so which is shown in the green and the red dots here. So you can see that SPHERex could potentially uniquely constrain the high redshift universe at redshift above 3 or so, which is would be very difficult to achieve with current, even with current and upcoming galaxy surveys. So eventually, what we're hoping to do is using multi-line, using all these multiple light intensity mapping and try to make a composite or comprehensive understanding of the universe. So shown here is basically what we thought will be happening at the high redshift during realization, we'll have density fluctuation, will be, they could be traced directly by ionizing sources, which could be traced by, the density fluctuation, the high peaks are the source ionizing sources, and they could be traced by H alpha and C2 lines. And then these lines will basically generate, will ionize the intergalactic medium, and then we can use the 29 centimeter to see the neutral part, which are dark here. But then we could also potentially see the emission from Lyman alpha emissions, which will scatter in between the partially ionized regions. So with multiple lines, we can basically piece out a comprehensive view of realization complementary to all the Galaxy surveys will provide in the coming years. Okay, so this is my summary. So I think I will say this already. So I think line intensity mapping is still a promising probe of cosmology, and especially the high-redshift universe. And this has been a booming field, and we really, again, thank Paul for his initial endorsement and support that to make all this possible. Thank you.
Thank you very much, Tzu-Ching. Questions? Time or SPHEREx?
So you mentioned that you may be moving the time instrument to CSO in the south. What's the timeline for that?
So CSO is currently being moved to Chile, but with time, we don't have a timeline yet because we actually need to modify the time instrument itself to for different atmosphere loading. So we basically, the Chile side is much better, so we need to change the barometer properties. We need to trim the laser legs, or we need to laser trim the legs to change the TC basically of the superconductor. So that part we are currently working on, and we don't currently quite have a timeline for that yet.
So there's been a lot of really surprising and exciting results from JWST in the last year, precisely the epoch of ionization, about everything about galaxies, and also mass metallicity relation about galaxies. So you need to produce your carbon, about bigger ions. So has that impacted your forecasts, both for this and for SPHEREx?
I guess not currently. I guess we were still, I think the jury is still out for all those high redshift candidates of JWST. I think if that's what you are.
Well, in detail, whether it's redshift 10 or 10.5, but there's no jury. I mean, we've seen the first epoch of galaxies, certainly beyond redshift 6 to 10.
Right. Yes, so I guess, yes, I agree, but well, I guess in any case, I think it's good news for us that there is star formation activities and their metal productions are very high redshift, which is great for us, but we haven't really quite updated that yet. But overall, I guess we haven't also, the realization history story is not, scenario is not, I think we are not at the stage of updating that yet, so I wouldn't think there will be major updates for now. But in any case, it will be in a great direction,
I have a similar kind of question as Louis. Some of the recent simulations I've looked at suggest that the CGMs are much more extensive, more metal rich. So I was curious in your forecast whether your C+ emission is based on individual galaxies or were you folding into possible CGM contribution?
Right, so the forecast didn't include CGM contributions, but there are definitely observations where with the diffuse C2 emissions, which would be great for us also, but we haven't modeled out components yet. No.
Okay, good. Thank you very much. So this concludes the high redshift and cosmology session, and then please come back after the coffee break at 4 for the Galactic Center. Thank you, everyone.